Hello, my name is Daniel Madrzykowski. Today we're going to be talking about the challenges of changes in materials and construction methods and how that impacts fire safety, how it impacts the ability of firefighters to operate in the fire environment, and what that means for people that occupy the buildings. I work for the UL Firefighter Safety Research Institute. FSRI is dedicated to adding to the knowledge base of firefighters to make them more effective, increase their safety in order to reduce injuries and deaths in the fire service, and in keeping them safer and making them more effective, that will in turn improve their ability to rescue people and keep the communities that they serve safe. Today's fire environment is not something that changed overnight. It's something that has evolved over the past 50, 60 years. In the United States, a number of the factors that add up to change fire behavior within residential structures are larger homes, open spaces, changes in fuel loads. Due to new construction practices and changing building materials, this also results in increased void spaces, smaller lots, meaning the property that the building is on. Bigger buildings are closer together. And then new technologies are always coming on the scene, whether it be energy technologies or insulating technologies or things like that, meant to solve one problem, but perhaps not taking the fire issues fully into account. Because in the US, the majority of the fire losses in terms of deaths and the largest number of fires are in residential structures, this talk will focus mostly in that arena. However, many of the things that are discussed and many of the materials that are brought up in the residential arena, you might also see some parallels to in commercial and industrial space. And in many cases, thinking about Grenfell, you may be able to apply these lessons or observations in that case as well. So all these things add up to fires that potentially are larger, grow faster, are hotter, result in flashover quicker, which means that there's shorter time to escape if you're inside the building. Given lightweight construction and some of the engineered lumber designs, that could mean shorter time to collapse. There's increased exposure problems because these larger homes are closer together. And then from the new technologies, unknown hazards. What's coming next? So let's look at each one of these. And again, this is with the lens from your friends across the pond in the United States. But I've got a couple of typical house photos, if you will. So if you look at a home that was built circa 1970, we would see that typically a single-story ranch. And the single-story ranch has been one of the most popular home designs in the United States over the past 70 years. And even the ranch itself has changed somewhat, but this is a very typical one. And it's on the order of 130 to 140 square meters. And as you can see in the graph that between 1973 and 2017, according to the US Census, the average size of a single family home has increased from about 150 square meters to over 230 square meters. So what does that look like? Well, for a single family detached structure, all the way on the left, we see the ranch home versus a new home, typically 2 stories with a basement. And we could see that the size is almost 3 times. This is very typical of what a detached home looks like in the United States nowadays in terms of new construction in a development. We look at the row homes, for example, homes that were built in the 1950s or after World War II in Baltimore, Washington, D.C., Philadelphia, areas like that. And they're typically about 150 to 167 square meters, accounting for, again, 3 levels, a basement, first floor, and a second floor. While the modern townhouses or row homes are in excess of 200 square meters. Then we look at, again, a standalone brick colonial from the 1950s, about 140 square meters, compared to what we would say, and this is a little bit of an extreme, but they are very popular in the Washington metropolitan suburbs, McMansion. And as you can see, that is over 650 square meters. So again, with regard to firefighting resources, what is being sent to fight the fire? These different house styles could be in the same first due for a fire department. Does the fire department change the response protocols in terms of number of firefighters and apparatus based on whether it's 140 square meters or 650 square meters? In most parts of the United States, I would say they do not. The other trend is we're not making any more land. And so to increase the availability of housing, to increase profitability perhaps in the development of the housing, the lot sizes on average have also been getting smaller over that period from 1973 to 2015. And so here's an aerial view of a single family detached home development that was built in the 1970s. It does not include any townhomes. And you can see that the lot sizes are ranging from 1,400 to over 2,000 square meters. Then a similar a housing development designed for a similar demographic, if you will, a similar price point in today's market. And you see that there's a mix of single family homes in the upper portion of the image, as well as row homes or townhouses in the same development. For the single family homes, those lot sizes range from 370 square meters to 550 square meters, keeping in mind those homes are much larger than the homes from 1970. So the result is larger homes closer together. And what we have seen time and again is that homes today, if the fire escapes the first house, by the time the fire department gets there, they could have 2 or 3 adjacent structures involved in fire, where that typically wasn't the case 30, 20 years ago. Inside our homes, we've changed how we like to live. We like more open spaces, open floor plan design. And again, that for the everyday life, that's perfect. That allows more functionality of the space. It's allows more connectivity within the home for the family, makes the living space more flexible. In some cases, that's easier to heat and cool. The bad news is when there's a fire in a home, as you can see in this image here in one of our test homes, that the fire in the living room can rapidly push smoke and heat into the upper level where the bedrooms are without any compartmentation. There's nothing to restrict the flow of the toxic gases or the flow of the heat or the flow of the flames even to stop them or slow them down before they reach the bedroom area. So again, when do people die in fires? Well, in many cases, the fires occur while they're sleeping. Some sort of ignition device was in the sofa, whether it's a battery charger that was left on overnight and improperly charging and overheating, or a defective battery, or cigarettes from smoking, discarded smoking material, something of that nature. Any of those things might lead to an ignition and potentially tragedy. One of the biggest changes in our homes are the changes in the types of fuels that are in our home. So in the video, what we're looking at is a cotton sofa on the left, and the cotton sofa has a cotton padding over steel springs because cotton doesn't hold its shape very well. The textile material covering the sofa is cotton as well. On the other side, the sofa that's mostly engulfed in fire at this point in time, the cushions are made of polyurethane foam wrapped with polyester batting and a polyester microfiber with the engineered lumber wood frame. And as you can see in the first 5 minutes, that fire pretty much has gone through the foam plastic material, and it reached a peak heat release rate, if you look on the graph on the right, of over 4 megawatts, peaking at about 5 megawatts briefly, while the cotton sofa is burning at 300 kilowatts the entire duration. And that's its peak. It never gets higher than 300 kilowatts. And it burned for more than an hour, where basically within 15 minutes, this fire had burned itself out. Now, the challenge, of course, is in our homes, there's never only one piece of upholstered furniture. So this piece of furniture would ignite other pieces of furniture and cause the fire to spread. It's not only in furnishings, it's there are changes to appliances as well. And this video, courtesy of the London Fire Brigade, shows how changes in design and materials can impact fire spread and fire hazard within a home. So here we have a refrigerator or a fridge freezer unit. And in one case, the freezer is encased in metal, in steel, and behind it is the insulating foam plastic. And on the left-hand side, we have the foam plastic where that unit is sold, where the foam plastic is exposed and the fire can readily get to it. And as you see, the flame spread and the heat generation, very much just like comparing the cotton to the polyurethane foam sofa, now we have a fridge freezer that is burning with it, will be burning with a heat release rate that in terms of the look of the flame, we might as well take a small piece of upholstered furniture made out of polyurethane foam and put it in the kitchen and light it on fire. So we certainly thank the London Fire Brigade for looking into that. And I know that why it's important to incorporate the fire service's experience in understanding fire hazard and understanding trends. The London Fire Brigade certainly noted trends in appliance fires or white good fires and how the hazard was changing long before the occurrence of Grenfell. Void spaces. In order to have this open floor plan or open concept design, engineers have designed different types of engineered lumber to make good use of the lumber that's available. They've used different types of structural design for engineered trusses, lightweight trusses that can create larger spans than in the older homes. For example, in the older ranch home, the maximum width of a room was typically 12 to 14 feet because with a nominally dimensioned lumber beam, 2 by 12 or so, that would be the maximum span that they would have between structural walls. But when you're using engineered trusses and joists, you could span 20 feet between walls or larger. Part of the payoff for that is, or the cost of that is, you may have to have a larger void space, a deeper truss, in order to safely span that larger range. And then, of course, when a fire gets in a void space, it's maybe difficult to detect, or if it starts in the void space, it may be difficult to detect early on. And it's certainly a more difficult fire to fight when firefighters arrive because the fire is trapped basically between a couple of fuel surfaces. And if it's able to get air, it can burn and spread very rapidly through the structure. And there have been many cases in the US where entire buildings, perhaps containing 100 units or 200 units, have, just due to a plumber's torch, for example, spread fire through a pipe chase and up into an attic that looks like a lumberyard in the sky if you look at the image in the upper right-hand corner, and basically destroyed the entire structure before the fire service was able to stop it. So again, changing building materials, we encapsulate our buildings in plastic. We put foam plastic as an insulating device to save energy. What we use is structurally has changed pretty dramatically. If we look at the center photo there, looking at the nominally dimensioned lumber that is currently available, look at the width of the growth rings versus a piece of lumber that's over 100 years old. Cut from an old growth forest, and you see that the growth rings there for that structural piece are very different. There are about 4 or 5 growth rings in the older wood compared to the newer wood for each one in the newer wood. And then we have an engineered wood I-joist. In addition to the structural members changing, the gypsum board, which we use to protect those structural members, has been changing. It's become lighter. Many manufacturers have made a lightweight version of gypsum board. That has resulted in a 30% decrease in weight. Again, there's a number of reasons why that decrease in weight is very good. But on the other hand, when it comes to fire, if we have reduced the mass and the fire hazard hasn't changed, that basically means that the fire has the potential to fail that sooner. New technologies, solar panels, for an example, here in these photos are on roofs. That changes firefighters' ability to do vertical venting. That increases the hazard for firefighters in ensuring that the systems are de-energized. We have technologies on our homes in forms of lithium-ion batteries, for example, that didn't exist in our homes 10 years ago. Things like the hoverboard that you see a flame in the image on the upper left-hand side, and then also commercially with energy storage systems where there are banks and banks of lithium-ion batteries in basically containers that are air conditioned and controlled. But we've had several instances in the United States where there's been a thermal runaway in a lithium-ion battery pack, and that has challenged the protection systems that are built into current energy storage systems, and in some cases have resulted in injury to firefighters that have responded when the systems have exploded. So all of this comes together in our lifestyle choices, and here 2 similar rooms. One room is composed mostly of natural materials, cotton, wool, and to the extent we could find it, wood that is not pieces of wood glued together, but real wood, sawn wood. And then we have the synthetic room, and that is composed of, as you might know, synthetic materials. Why do we call them synthetic materials? Because they're synthesized from petrochemicals. And so we have our foam plastics, our polyurethane foam sofa. We have a polyester blanket laying there. Again, there's polyester microfiber on the sofa, polyester curtains, whereas everything in the natural room typically is a natural fiber. So you see that we have a pretty dramatic difference in fire growth rate in the rooms. Not only that, look at the excess fuel that's represented in the dark smoke, the soot in the smoke that can burn again when that smoke will auto-ignite and light. And we see the flames starting to roll the ceiling in the synthetic room, and now we're transitioning to flashover. And basically nothing survives flashover. Most things will burn. There are very few things many things are fire resistant, but few things are fireproof. And certainly people cannot withstand the amount of toxic gas that's generated. So we've done this example a number of times, and you see the comparison between the times to flashover, basically a change in a factor of 10. Or in some cases, within that 30-minute period, the natural room didn't flash over at all. We have a solution to all this. It's residential sprinklers. I know there's going to be another talk on that, but I just thought I'd point this out. This is from a test series that we did on basement fires as an example. And as you can see, out of the 12 experiments, we had temperatures that were well in excess of tenable conditions for humans. In some cases, several hundred degrees C, 380 degrees C, up to almost 1,000 degrees C, as temperatures at about 4 feet off the floor. And look at the oxygen concentrations. And again, the oxygen concentrations in most of the experiments are below 12%, which is the level on oxygen alone where you would expect a person to have the potential to go unconscious in a short period of time. But keep in mind the synergistic effect with carbon monoxide and carbon dioxide increases, and hydrogen cyanide that would be coming from the foam plastic and the polyurethane. And it's a pretty toxic mix. So basically, in all these cases, we have untenable conditions except for one. And experiment 10 is where sprinklers were used. The peak temperature, 40 degrees C, and the oxygen concentration never got below 18%. You can see the damage in the picture on the upper left, where the damage was limited to one sofa, the sprinkler activated and wet everything down and shut the fire down and made it tenable certainly throughout the house. How can you learn more about this? And in our other research, we have a Fire Safety Academy now, a legitimate learning management system, which you can access for free. And we have a wide range of topics, from firefighting tactics to heat transfer and fire measurements, as well as looking at decon, or basically how to limit your cancer exposure on the fire ground. We have issues on residential attics and exterior fire hazards and things of that nature. We just finished this online basement fire training course that I shared the sprinkler slide with you on, and I would encourage you to take it. We're pretty proud of it. We've used some new technologies and new techniques in the class. And you can look at not only our research efforts, but our public safety efforts with regard to closing your doors at night, and using smoke alarms, and planning your egress path, so things for the public as well as for firefighters. We also have some STEM activities going on for middle school children with UL Explore Labs, and I'd encourage you to go to that site. And again, all of this material is in the public domain and is free for your use. Thank you very much.